Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures in computer architecture. We are now looking at the memory subsystem. We had already looked at the cache subsystem within the memory subsystem, and now we are looking at the virtual memory. In the previous lecture, we looked at why virtual memory is needed, basically to increase the size of the memory subsystem as a whole, and we also looked at how it is implemented. So, in the details of the implementation, we saw how we use page tables, and we use a concept called address translation, where we map a larger virtual memory address to a physical memory address which is smaller than that. So, this is what we have covered in the previous lecture. So, what we will look at today is some more details on the virtual memory system, and we will look at the use of a structure called translation look-aside buffer, which helps to improve the performance of the virtual memory system. We will also look at certain replacement strategies, and we will also look at some memory management issues that come up. So, a quick review of what we have in terms of address translation. So, remember we have a virtual address which comes from the processor, which consists of a virtual page number plus an offset. Now, this virtual page number part is used to index into a page table, and the location of the page table is specified by means of a page table base register. So, this gives me the page table base address. The virtual page number indexes into this page table, and once we index into the page table, the corresponding entry over here will give me the starting address of the physical page if it is present in memory. And whether it is present or not in memory, I will know by looking at a valid bit which is there as one of the control bits here. So, if the valid bit is set, I know that this page is available in memory, and the corresponding entry is giving me the physical memory location. So, I add that physical page number to the offset to get the complete physical address in the main memory. So, this we remember, this is what we do in terms of the address translation. There are certain issues that we need to look at in doing this address translation. Okay. One is that if we look at how this address translation actually gets done, it appears to require lots of memory references. Now, why do I require lots of memory references? Because before I do the translation, I need to first of all access this page table entry. And where is this page table going to be located? This page table itself will be located in main memory. So, if this is located in main memory, so to do this translation, I need to first access this page table, get this location, then again access the physical main memory in order to get the actual data that I am looking for. Okay. So, you can see that there is, and if there are many reads and writes that are taking place, right, for every read and write you need to do this operation. We need to look at what we can do with this page table. How do we improve the performance, or how do I reduce the number of accesses that I can do to the page table? So, this is where we try to use a small technique which is very similar to that of a cache. Now, remember, whenever we talk of cache, we look for something called locality of reference. That is, if a particular location is accessed, we want that location to be accessed again frequently. If that happens, then we say that it has a good locality of reference. So, similarly, we find that page tables also have good locality of reference. That is, if a page table is accessed for a particular memory access, let us say, it is quite likely that the same page table is going to be accessed again and again. So, now, what we can therefore do is, you can use a kind of a fast cache of the page table entries and put it within the CPU itself. Okay. So, this fast cache of page table entries, that is, I am saying that if there are certain number of page table entries which are being accessed frequently, those page table entries are taken and put within the special location in the CPU itself, which is called as the translation look-aside buffer. Okay. So, you can see that the name kind of explains what it is expected to do. It is a translation buffer. Okay. It is a small buffer which is meant for translation. We call it as a look-aside buffer because you look into it before you actually go into the memory to access it. So, you look aside, look for this entry, if it is available you take it from here, otherwise you will anyway have to go to the page table and get it from the page table. Okay. So, typically if you look at how this is expected to improve performance, if we look at certain figures here, for a 16 to 512 page table entries, if we assume it takes 0.5 to 1 cycle for a hit, and 10 to 100 cycles for a miss, okay, then you get, and you have a miss rate of about 0.01% to 1%. So, with this kind of a TLB structure, you find that you are only having about 0.01% to 1%, that is 100th to 1% of a miss rate that you have. Remember what we mean by miss rate. Miss rate is the number of misses that you get, average number of misses that we get per access, okay. And these misses are typically handled both by hardware and software, or by hardware or software. You have both solutions to handle these misses. So, once I have this kind of a small translation look aside buffer, which is a special kind of a cache, which is used to store these page table entries, we can see that the number of actual memory accesses to access the page table entries will be reduced, okay. So, this is the idea that we are using here. So, if we look at the details of how this gets implemented. So, if we look at how fast translation is done using a TLB, right. So, this is the structure that we are showing here is the translation look aside buffer. So, what it has is a mapping between the virtual page number and the page frame in memory, that is the virtual memory address to the physical memory address mapping is present in this TLB. So, this works just like a normal cache. So, what we will have is the virtual page number which is coming from the processor, which is taken from the virtual address. This page number is taken and this is compared with all the page numbers which are there here simultaneously, okay. So, we are looking at a fully associative TLB. So, this fully associative indicates that any page number can sit in any position. So, we need to do a full comparison of all the entries which are there in the TLB. So, all the page numbers which are here are compared with this incoming page number. If there is a match in any one of the entries, it is a hit. If there is no match in any of the entries, then it is a miss, it is a TLB miss. So, if there is a TLB hit, then the job is very simple. We just go to, we take the corresponding value of the physical address, the page frame from the TLB. To that we add the offset and generate the physical address in main memory, okay. This is what we do. If it is not there, it is a miss, then we have to go and actually access the page table from main memory and then access the actual location that we need to access, okay. So, this is the process that we do when in the presence of a TLB. A quick look at the overall process. So, we can see that the virtual page number is given to access the TLB. So, in the TLB, if we see, you have the control bits and then the tag is where the page number will be stored. This comparison of all the tags is done simultaneously and we get the physical page address from here. If it is available, this is going to point directly to the physical block in the physical memory. If it is not there, then I go to the page table. Remember, the page table will tell me whether it is valid or not. If they are valid addresses, it points to the physical memory, otherwise it will be pointing to the disk storage, right. So, this is the overall structure that we have. So, we can just look at a little bit more of details. So, the virtual page number, if you look at what we have in the TLB, in the translation look aside buffer. So, we have 3 bits that you can see over here. We have a valid bit which indicates whether this particular entry is valid or not. Then we have a dirty bit and then we have a reference bit. This reference bit is used to indicate whether this particular entry has been accessed recently or not. So, whether it has been referenced or not. This again is useful when we need to replace a particular entry from in this TLB. Remember, size of TLB is small, so we may be bringing in new entries, and when we bring in a new entry, we may have to replace an entry. So, we typically replace an entry which has not been referenced for a very long time. So, this reference bit is used to indicate the recentness with which we have accessed a particular location. So, then you have the tag. This tag will be essentially the virtual page number and then the physical page address, right. So, this is what we have in the TLB. Similarly, we have seen this in the page table already. The page table will again consist of a valid bit, dirty bit and a reference bit. Remember, this is not a cache, right, this is just a table. So, the entry into this table is obtained, the index into this table is obtained from the virtual address by adding it to the page table reference address, and depending on whichever entry we are pointing to, if it is available in main memory, we access it from main memory, otherwise we get it from the disk storage. So, this is the overall process that we have, okay, the details of what we need to understand with how everything works with the help of this translation look aside buffer. So, the question now is what happens when we have these TLB misses. Similarly, what happens when we have the page faults. Okay, we need to understand these things now a little bit more in detail. So, if you look at a TLB miss, if the page is in memory and it is a TLB miss, then what we need to do is we load the page table entry from memory and we retry. Okay. So, this could be handled in hardware Okay, it can get more complex for more complicated page table structures, but it can be handled also by software. Okay, how do I handle it by software? Typically, what will happen is when you get a TLB miss, it will raise a special exception called the TLB miss exception, and this exception will be handled by a handler, which could be written as part of your OS or whatever. Okay, so that is handled separately. So in case of a TLB miss, we need to get the load the new PT entry from memory and then continue with the access. Okay. If the page is not in memory, that is if it is a TLB miss and we also have a page fault. Okay, so what do we do this? Now remember, there are two things to be done. One is we need to fetch first of all the page from the hard disk or from the secondary storage and bring it into main memory. Okay, so the OS will take care of that normally. So the OS will handle the fetching of the page and updating the page table appropriately. Okay, then it will restart the faulting instruction. And when we do this, when the page table entry is updated, you can also update the TLB entry appropriately. So once you update the TLB entry and when we restart the faulting instruction, you will find the corresponding entries available in the TLB, and from there we can access it from the physical memory and directly continue. Okay. So this is how we handle a TLB miss. Now this TLB miss handler that we are talking about, right? I said there will be a special TLB miss handler. What this is expected to do is, we need to recognize a TLB miss before the destination register is overwritten. Okay. Now let us understand this a little bit more. So what we are talking about here is, when you are doing a data access, let us say I am accessing some data which I need to use, process it, do some addition, whatever, some operation on it, and then I am going to write some register or some value based on this. Now when you are trying to do the access, we should make sure that this TLB miss is recognized, right, and also handled before the destination register is overwritten. So which is why as soon as the TLB miss occurs, you have to raise an exception, and this exception has to be handled within that instruction. That is, normally when we talk of exceptions, we talk about handling exceptions within an instruction and between instructions. Now this kind of an exception is one that needs to be handled within the instruction. That is, that instruction when it is getting executed is raising an exception. So that exception first has to be handled before you can complete that exception. So that is what we need to be careful about when we are handling TLB misses and these kind of exceptions. So we will take a short break and come back and continue with the details. Welcome back after the break. So we looked at what happens in the case of a TLB miss. Now let us look at what happens in the case of a page fault. That is, there is a miss for a page. Okay, so what does a page fault handler normally do? We use the faulting virtual address to find the page table entry, and you locate the page on disk and you choose which page has to be replaced. Okay. And when we do the replacement, if the page that you want to replace is dirty, that is, it has been written to, then we have to write to disk first. Okay. So you write to disk first and then you bring in the new page. So then we read the page into memory and update the page table. So this is what is expected of a page fault handler. Now normally when a page fault is handled, that particular process will have to be stopped because it is a long latency operation that takes place. So you would have stopped that process, so you need to make that process runnable again and restart from the faulting instruction. Normally page faults are handled by the OS. Now what is the penalty that we have when you have a page fault? Okay. That is the amount of time that is spent when a page fault occurs. Remember what we need to do on a page fault. You need to fetch the entire page from the disk. Okay. And this can take millions of clock cycles, which is normally handled by the OS code. So what we also therefore need to do is we need to try to minimize the page fault rate. Okay. So how do I minimize the page fault rate? There are two things that we do. One is that we use a fully associative placement. Obviously, this is an obvious decision because when we are placing a particular page, when we bring a page into memory, you can place it anywhere in the physical memory. Okay. We do not restrict any location as we do in the case of direct mapping and so on. So we use a fully associative placement. It can go anywhere in the main memory, and we also go for some smart replacement algorithms so that the number of page faults are minimized. Okay. So this is something which is normally taken care of by the OS, but it is useful to understand what exactly happens here. So when we talk of replacements and writes, okay, this is to reduce the page fault rate. One of the replacement algorithms that we use is the least recently used replacement algorithm or the LRU replacement algorithm. So what does LRU indicate? It indicates that this particular page has not been recently used. So the page which has not been used recently, or which is the least recently used page, is the one that is picked up for replacement. So how do we identify this? This is normally done with the help of what we call as this reference bit. Okay, it's also known as a use bit, so in some literature. So this reference bit that we saw in the page table entry is set to 1 on access to a page. Okay. So whenever a page is accessed, immediately that bit is set to a 1, and periodically all these reference bits are set to 0 by the OS. Okay. So what will happen is a page with a reference bit equal to 0, okay, indicates normally that it has not been used recently. If it was used recently, that value would have been set to a 1 when that particular access took place. Okay, so you can see how this is implemented in a very simple manner. Ideally speaking, to find which was the actually least recently used entry, we will have to maintain a set of timestamp, or you have to maintain a set of counters and look at how the entire or find out the actual time at which a particular page was used, and then do a time comparison and so on. All that can be very complicated and very time consuming. So what is normally done is this very simple procedure, and all we use here is just a single bit. So one bit is used, and using that one bit, just set that bit to a 1 whenever a page is accessed, periodically clear it to 0. Okay. So if a page has not been accessed for quite some time, that value will remain at 0. So other bits which have been accessed, pages which have been accessed, will have their reference bit set to 1. So among the ones that have a value of 0, you can pick any one and think that that is and identify that has not been used recently, so that can be replaced. Okay, this is a very simple technique that is used for LRU. And if we look at write through versus write back, you can very easily see again here that write back is the only practical option. Write through is definitely not a practical option. Again, because you can't be writing individual locations at a time, because every write to disk will take millions of cycles. So you can't be doing individual write locations. That is, remember what we do in the case of write through. Write through indicates that when I write into the higher level of the memory hierarchy, that is when I write into memory, I should also write into disk. Now this is not practical, because every time you write to memory, you can't be writing to disk, it will take a long time. So the only practical option is write back. And when do we write back? We only write back if there is a write has actually happened on this particular block, and that is indicated by means of the dirty bit or the modified bit. So if the dirty bit is set in the page table entry, then that particular block has to be written back, otherwise it need not be written back. This is how we handle the replacements and writes. Now another aspect to understand is the interaction that we have between the translation look aside buffer and the cache. So if we look at the interaction between the TLB and the cache, so just look at the various steps that are taking place. Your process producing a virtual address or a logical address. Now that we have to put it through a TLB, get the physical address, and then use that physical address to check whether it is there in the cache. Okay, if that address the block for that address is already in the cache, we can take it from there. So I will go to the cache using that physical address and then do an access. If it is not in the cache, then of course I will go to main memory. So this will be the process that you will have when you also have this TLB in place. Okay. Now if the cache tag uses physical addresses, remember that this translation needs to be done before the cache lookup. So if you look at how the whole thing will be organized, you will see that this is what will take place. Okay. So you have the virtual address divided into virtual page number and page offset. Now this you can see is used to access the TLB. So the virtual page number directly is compared with all the tag bits here that you have in the TLB. If it is a TLB hit, okay, you get the physical page number from here, and the physical page number is given to the cache, right? To the physical address is given to the cache for it to access. Okay, so you can see that this physical page number now will be divided into a cache index, block offset, byte offset for accessing within the cache block, and that you can see another tag access that is taking place here. This is the checking whether it is there in the cache as well. So you can see that there are actually two accesses that will have to take place. One is the access in the TLB to get the corresponding address in the cache, to get the corresponding physical address. Then using that physical address, I have to check whether this particular physical address is available in the cache. So I will do another tag comparison of the cache for that. If it is available in the cache, then I take it from the corresponding block in the cache. If it is not available in the cache, then I go to main memory. Okay, if it is a cache hit, then there is no problem, I can take it from there. Otherwise a cache miss will occur, and then we need to look at the other aspects that we have with respect to a cache miss. Okay, so this is what we do. Now another option that we could use, another alternative that we have is, instead of having the cache being addressed using physical addresses, you can also address the cache using virtual addresses. That is also another possibility. So, that is, you use a virtual address tag for the cache and check the cache using the virtual address tag itself. But there can be some complications that can arise here, which is that you can have different virtual addresses for the same physical, for a shared physical address. So, there are certain complications that come up in this case, but you need to be aware of this kind of a complication that can occur when you use this. But if we do not use virtual addressed cache and we use only a physically addressed cache, we have to remember that there are two accesses that will actually take place. One is a TLB access, which also is a fast access, and then the actual cache access before the cache can be used. So, when we look at virtual memory plus cache, we need to understand that there are certain other complications that need to be handled correctly. The next issue that we need to understand is when different tasks are sharing the same address space. So, remember that we can have, when we talk especially of a multitasking system and so on, there are multiple tasks which can be simultaneously running on the system, and each task will have the entire virtual address space to itself. Okay. So, which means, but they are sharing the same physical space. Okay. So, what will happen is that you will have to provide for some kind of a protection between these different processes. That is, you can't have, since they are sharing the physically available space, you have to make sure that one process, the address of one process does by mistake is not mapped onto an address of another process. Okay. So, we need to provide some kind of a memory protection in this case. So, this is normally done with the help of OS assistance, and this memory protection is normally handled as part of our virtual memory system. So, which is why we need to understand this also a little bit. So, if we look at this memory protection, what is normally done is that normally you will have some support from hardware in the form of what is called as specialized modes of operation. So, normally you have what is called as a privileged supervisor mode, also known as the kernel mode of operation, and there are some special instructions which can be executed only in the privileged mode of operation. So, we have what are called as privileged instructions. Okay. And accessing the page table and other state information is also normally available only when you are the supervisor mode of operation. For example, if you try to access a particular page table and you do not have access to it, that is, if you are not in the supervisor mode, it will cause an exception, and that exception will be handled by the OS. Okay. So, with the help of this kind of a privileged instruction, it will be only the OS which can handle, which can update the page tables and which can update all other state information. So, once you provide this kind of a protection, you can make sure that no other processes can change any entry in the page table. So, that is one part of the protection. Okay. So, other things that we do is that you also have to provide for different address spaces for the different processes. To do that, what we do is the following. So, as I said, the entire space that we have, which is used by the operating system, is referred to as the system space, and the operating system's space is considered to be different from what is used by the user, which is called as the user application space or the user space. Okay. And your entire virtual address space can be looked at as one system space which will be used by the operating system plus several user spaces, that is, several users can share the rest of the space that is available. Now, the way the operating system will allow multiple spaces, multiple user spaces to coexist is in the following manner. So, what the MMU will do, as we have seen, it uses the page table base register to determine the address of the page table, right, that is to be used in the translation. So, what we actually do is different page tables can be maintained for the different processes, and it is a job of the operating system to switch from one page table to another page table when it is switching from one process to another process. And how do I switch from one page table to another page table? All I need to do is I have to change the contents of the page table base register. Remember, the page table base register is the one that is pointing to the page table. So, if I change the page table base register, I can switch from one space to another space. Okay. So, this is basically how the operating system will allow you to change it, to go from one space to another space. Now, remember that at any given time the page table base register can only point to one page table. Okay. So, only one page table can be used in the translation process at a given time. So, there is no possibility of one processor's page table being mixed up with another processor's page table. That is the basic idea that is used over here. So, now that we have looked at how the virtual memory subsystem handles these various issues, it will be good to summarize and take a look at the memory hierarchy by looking at both the cache system as well as the virtual memory subsystem. If we take a look at the big picture and look at certain common principles that are used, it will help us to consolidate the idea of how the memory hierarchy works. Okay. So, at each level in the hierarchy there are 4 points that we look at. We basically divide the entire thing into blocks and we deal with movement of blocks of data. So, the 4 questions that we ask is, where do I place a block? Second is, how do I find a block? Third is, how do I replace a block on a miss? And what is the write policy? Remember, these are the 4 points that we talked about even with respect to cache. The same points are looked at with respect to virtual memory subsystem as well. Now, we have seen that for block placement it is determined by associativity, direct mapped, n-way set associative and fully associative, which are used in the case of cache. But in the case of hard disk it is only fully associative which is used. That is in the case of virtual memory system, from hard disk to main memory, that is the virtual memory subsystem, it is only fully associative which is used. And we know that higher associativity reduces miss rate, it increases the complexity and cost and the access time, but it will give you a better performance. If we look at replacement, replacement is done by means of LRU or random replacement. Now, LRU is one which is again complex and sometimes costly hardware is required for high associativity, but we also saw how in the case of virtual memory subsystems a simple 1 bit reference bit is used to implement the least recently used policy. Many other processors also use the random replacement policy, which is actually very easy to implement because you just pick one block at random and replace it. And it is also found that LRU almost gives you as good a performance as random almost gives you as good a performance as LRU. And for virtual memory, LRU approximation has been used as well as with some hardware support. Okay, that is something that we have seen. With respect to write policy, we know that there is only a one policy available for virtual memory, which is write back, whereas write through and write back can be used for cache. So, with these 4 points, if we are able to understand what happens in the case of virtual memory and cache, your understanding of the entire memory hierarchy will be complete. So, to summarize, what we have looked at so far in today's lecture are the following. We have looked at fast page translation using TLBs. We looked at what a page fault handler is expected to do. We looked at some replacement strategies, and we also looked at some memory management issues. So, a set of questions to review the contents covered today. Question number 1, how is the page table located? Question number 2, what is a page fault? How is it handled? Question number 3, why do we need TLBs? Question number 4, what happens on a TLB miss? Question number 5, what is the commonly used page replacement policy? Question number 6, what are the tasks involved in memory management? Thank you.